Okay, so welcome to the next in our series of videos on solving systems of linear equations for Math 1410 linear algebra. So this next video is going to introduce the main algorithm that we use for solving a system of equations. It's called Gaussian elimination, named after Carl Friedrich Gauss, who was a famous 19th century mathematician. The idea with Gaussian elimination is, well, what you're eliminating is you want to eliminate some of the variables, right? So basically you want to, by combining the equations in clever ways, you want to get rid of some of your variables, allowing you to solve for the ones that remain, right? So beginning with this system, we've got three equations with four variables here. What we might want to do is kind of reduce things down to maybe reduce it down to say two equations and only three variables, and from there maybe down to a single equation relating two of the original four variables, to allow us to sort of set up and solve. So the way we do this is as usual, we want to set up our augmented matrix because it's easier to work with an augmented matrix than it is to keep all the variables in place. So we set up our augmented matrix like so. 2, 1, 0 for the x's, 0, 3, 2 for the y's, 6, 0, minus 1 for the z's, for the w's, 2, minus 2, 1, and over on the other side go our constants, 4, minus 1, 1. Alright, so at this point I want to create a leading one. Now I've got two options sitting here for creating a leading one, and I can use whichever one I want. What you want is you would like to create a 1 in the upper left-hand corner. We'll see why this is useful as we move forward through the example. There's two ways to do it. I could either swap row 1 and row 2 because I notice that I have this 1 sitting here. I could swap rows to move that up. Or I could take the entire first row and I could divide everything by 2. I notice that, hey, everything in row 2 is even. Why don't I divide by 2? Either one is valid. Why don't we divide by 2? Why not? So what we might do here is we might say, let's do 1/2 row 1 and make that our new row 1. Okay? So I get 1, 0, 3, 1, 2, and then 1, 3, 0, minus 2, minus 1, 0, 2, minus 1, 1, 1. Okay, so now I've got that 1 sitting there. So this guy is called a leading 1. And you want to use your leading 1 to create zeros. And where do you create zeros? Well, you create zeros in the column containing that leading 1. So you get rid of any non-zero entries that are below that leading 1. And, well, there's only one non-zero entry below the leading 1. It's the 1 directly below it. How do I get rid of that 1? Well, if I subtract row 1 from row 2, I'm going to get rid of that 1. So I want to do row 2 minus row 1 and make that my new row 2. Okay, so that gets me 1, 0, 3, 1, 2. 0. 3 minus 0 is 3. 0 minus 3 gives me minus 3. Minus 2 minus 1 gives me minus 3. Minus 1 subtract 2 gives me minus 3. 0, 2, minus 1, 1, 1. Okay, and well, you can probably guess what I want to do next. You can tell this problem was a bit of a setup. I made sure that all those 3's showed up. Most of the time, if life hands you a system of equations, it's not always going to work out so nicely, but we'll stick with artificial examples because they take less time. So the next thing I'm going to do, I'm going to divide the second row by 3. I'm going to multiply through by 1 over 3. Get rid of all those 3's that are sitting there, right? That's going to give me my second leading 1. So 1, 0, 3, 1. I haven't changed the first row. Now I divide everything by 3. So 1, minus 1, minus 1, minus 1, 0, 2, minus 1, 1, 1. Okay. Now I have two leading 1's. Okay. So I keep these guys there. The idea, what we do in this algorithm is we basically try to build up sort of a staircase of leading ones. We work our way down and to the right, starting from the upper right-hand corner. So the next thing I can do is I can say, well, look, I've got this leading one. I'm going to use it to make zeros. So I look what's sitting below the leading one. There's a 2 sitting there. I want to get rid of the 2. How do I get rid of the 2? I take row 3 and I subtract off 2 times row 2. 2 minus 2 will give me a 0. That's going to become my new row 3. So I'm leaving row 1 alone. Let's recopy that. I'm leaving row 2 alone, so we recopy that. Okay, and now 2 minus 2 gives me my 0. Minus 1, so everything else multiplied by minus 2 is going to give me a plus 2. So minus 1 plus 2 gives me a 1. 1 plus 2 gives me a 3. 1 plus 2 gives me a 3. Okay. And, oh, look, leading ones all the way down. Okay. That's the best we can do. I mean, as far as trying to create these leading ones, that's as far as we can go. There's nothing else I can do from this point to create further leading ones because I've run out of rows, right? So the idea with this leading one, we'll define these in a bit, but basically the leading one should be the first non-zero entry in your row. Well, I've got leading ones in all 3 rows, so that's pretty much the best I can do. So where do I go from here? Well, what I can do from here is I can say, well, what are these equations that are left here, right? So one of the reasons why these leading ones are nice is the equations that remain are, so the first one is x, okay, plus 3z plus w equals 2. That 1 in front of the x means it's very easy for me to solve for x. X is going to be 2 minus 2z minus w. Okay. In the next row, I've got y minus z minus w equals minus 1. Again, the fact that the coefficient of y is equal to 1 means I can quickly solve for y. Y is equal to minus 1 plus z plus w. And the last one says z plus 3w is equal to 3. Okay. And so I get, I get w, z is equal to 3 minus 3w. Now, one of the things I can do here, if I wanted to kind of continue with this, we're gonna leave it at this for now. But if I wanted to kind of continue, what I could do is I could take this value for z, right, and stick it in here. Right? Then y would be written in terms of w only. Then I could take this value for z and I could stick it in here, and then z would be written in terms of, or x would be written in terms of w only. In fact, let's do that. Okay. So x is going to be equal to 2 minus 2 times 3 minus 3w minus w. So x is equal to, that's 2 minus 6 minus 4, and then 6 minus 1, minus 4 plus 5w. Y is going to be minus 1 plus z, so 3 minus 3w, plus w. So y is equal to 2 minus 2w. Okay. All right. So that gives me, let's kind of rewrite the x and the y. Okay. So I get, here's x, here's y, okay, and down here is z. Okay. Notice that all x, y, z, they've all been written in terms of w, right? I don't have any equation that says w equals something. The w in this case, w is what's called a free variable. It's a free parameter. Okay, w can be whatever it wants, but once we choose a value for w, then I have to accept values for x, y, z, right? If I choose, say, w is equal to 1, then x will be minus 4 plus 5. X would have to be 1, y would have to be 0, z would have to be 0, right? So that's one possible solution would be x is 1, y is 0, z is 0, w is 1, and you could check that works in all three equations. But in fact, any other value for w would do. Okay, so we'll see that this comes up quite a bit, and because w is free, w could be any real number. We can see that you get an infinite number of solutions to this system. Okay, so this is basically the idea. So how do we kind of solve, right? So somebody hands us a system of equations, right? We want to simplify and, if possible, solve using these elementary row operations, right? So same as we did in this previous slide, right? The way I solve this system is I write down my augmented matrix and I use my row operations to try and get my augmented matrix down to a simpler form. And a simple form is going to be one that has a lot, as many ones and zeros in there as we can manage. Okay? And so basically what we want to do is we want to use our row operations to get this thing down to a simplified form, and from that simplified form, read off what the solution to our system is. The only thing is we have to agree, first of all, on what is the most desirable, simpler form, right? If we're going to program a computer to use this algorithm to solve a system, we have to tell the computer when the algorithm terminates. When do we stop? When do we know that we're done, right? So that's one thing we got to know, is when do we finish? The other thing is, okay, how do we program this algorithm as efficiently as possible? If we're dealing with thousands of equations and thousands of variables, we don't want to mess around, right? We want to, minimize the amount of computational power that's going to be needed to solve this system. Okay, so we'll answer the question about when to stop first. So the question of when to stop is this row echelon form. So the row echelon form, this is this sort of, this simpler form that we're looking for. Okay, so how do we know when our matrix is in row echelon form? Well, it might happen, it didn't happen in the previous example, but it could happen that one of the rows in your matrix cancels out completely and you're left with just a row of zeros. If you end up with a row of zeros, you throw it down to the very bottom of your matrix, right, where you can ignore it. We don't care about rows of zeros, they tell us nothing. The next condition is that for a non-zero row, so if a row has at least one non-zero entry, we want the first non-zero entry to be a 1. And by first, we always read things left to right. So first we mean, the first entry reading from the left, right, when we say first. So reading across the row from left to right, we want the first non-zero entry to be a 1. This is our so-called leading 1. And as we kind of work our way down, right, any sort of new leading 1 needs to be to the right of any leading ones that we already established. So let's jump back to what we had here, right? We can see that here, that the first leading 1 is furthest to the left, and then as I go down, each successive leading 1 shifts over to the right. Now, it could happen, it doesn't in this example, but it could happen that as I go down from one row to the next, I shift over several columns to get to the next leading 1. There might have been a 0 and a 0 and a 0 and a 1, something like that. But I need to move at least one column over to get to the next leading 1. The next leading 1 is always over to the right. Okay. So these are the conditions to be in row echelon form. Now, row echelon form is simpler, but it's not the simplest. Okay, the reduced row echelon form, right here, the reduced row echelon form, this is the simplest. Okay. The simplest that you can get. You can't go any further than reduced row echelon form, right? So this is our termination point. If we get down to reduced row echelon form, then we're done. Okay. Now, if we jump back to the example we've already done, okay, we gave a matrix which is in row echelon form. Let me show you that. Okay. So why is it in row echelon form? It's in row echelon form because, well, there are no non-zero rows. We don't have to worry about that. Each row, the first non-zero entry in each row is a 1, and the leading ones follow this staircase pattern, right, of going, as I go down, I go to the right. Okay, so that means I'm in row echelon form. What do I need to be in reduced row echelon form? I need this condition here. Every leading one has to be the only non-zero entry in its column. So, what's missing? Why is this not in reduced row echelon form? Well, we look at this column here, right? The first leading one, it's by itself in its column. Every other entry in the first column is 0. In the second column, we've got a leading one and everything else is 0. But in the third column, I've got a 3, I've got a -1, right? Those guys are non-zero, and because those guys are non-zero, that's why I had to do this, this extra work up here, right? That forced me to do this extra work, right, where x depended on z and w, y depended on z and w, and I want them to depend on w only, and I had to do this extra step of substituting things in and simplifying. So if I decided to go and do a couple more steps, and why don't we do that? Let's actually let's do these additional steps. So let me erase all this. Okay. I'm gonna do 2 more steps. What am I gonna do? I'm gonna do this. I'm gonna say, well, to be in reducer echelon form, I gotta get rid of the 3. I gotta get rid of the -1. So I'm gonna do row 1 -3 row 3 into row 1, right? Because that's going to get rid of the 3 for me. If I do row 2 plus row 3 into row 2, that's going to get rid of that -1. I'm going to get, so 0, 0. So the bottom row is unaffected. Okay. Now, here's the thing. Because I've already, because the leading ones follow this staircase pattern, I don't have to worry about what's going on in columns 1 and 2. Those are going to stay the same because in columns 1 and 2, I'm using row 3, right? I'm using row 3 to create my zeros. But row 3 has zeros in those first 2 columns. So I don't mess up the work I've already done, right? I don't want to put things back where I already have zeros. I want to keep those zeros. But now I know that I get zeros here and here. Okay? So if I do -3 times row 3, it gives me a -9. Added to that 1 gives me -8. Okay. And I do, there we go, and then -1 plus 3 gives me a 2. Okay, good, good, good. So I get down to there, and I got to deal with the other side as well. 2 times, so I'm doing -3, right? So 2 minus 9 gives me -7, and -1 plus 3 gives me 2. Okay. And then if I kind of want to read off my equations, and I'm suspecting that I made a mistake somewhere because I'm not getting back to where I had before. This one here still says that z plus 3w equals 3, so I can immediately solve for z, 3 minus 3w, the same as before. The second row says y plus 2w equals 2, so I can solve for y, it's 2 minus 2w. The top row, here's where I must have messed up. X minus 8w equals -7, so x should be -7 plus 8w. It's not what I got before. So where did I go wrong? Oh, I can see where I went wrong. This should have been a 3. That 2 should have been a 3. And so then, yeah, so then 2 minus 9 should have given me, let's fix it, should have given me -7, and then -3 times -3, that's +9 minus 1, I get my 8, which agrees with what I had down there. Okay, so reduced row echelon form saves you the trouble of having to do this additional back substitution step that we had to do when we first did this example. Okay. All right, so additional terminology, I mean, you'll see this used, don't worry too much about it, but you'll see it used at one time or another. These columns containing leading ones, these are sometimes called your pivot columns. The corresponding variables are sometimes called pivot variables, sometimes called basic variables, sometimes called dependent variables. Variables that correspond to columns without a leading one, that would be the W variable in the example we just looked at. These are called free variables. Sometimes we call these guys parameters, free parameters. Okay, their value, we can choose any value we want for these guys. Sometimes we call them independent variables. You'll see a number of different terms in use for these guys. Okay. Now, here's some examples just to make sure that we have this idea of row echelon form, reduced row echelon form in place. Let's see if we can identify whether these guys are in row echelon form, reduced row echelon form, or neither. So the first one, is it in row echelon form? Well, let's see. Any rows of all zeros? No. Two non-zero rows, do they both start with a 1? Sure. Here. The leading one in the second row is to the right of the leading one in the first row. That's one of the requirements, right? The leading ones descend down and to the right. So this guy is in row echelon form. However, there's a 2 sitting above the second leading one, so that second leading one is not the only non-zero entry in its column, so it is not reduced row echelon form. Okay. What about the second one? Well, let's see. There's a row of zeros. It's at the bottom. Does every non-zero row begin with the leading 1? Yep, here. Okay. Notice the first column is all zeros. That could happen. You might think, how could that possibly happen? We'll run into situations later on where this does happen, right? There's nothing in the definition of reduced row echelon form or row echelon form that says you can't have a column of zeros, and certainly nothing saying that the first column can't be 0. So don't worry, it might happen. If it happens, well, what does that tell you? As far as solving the system, that just tells you that that first variable is completely free. Basically, the only way this really happens is if the first variable just does not show up in your equations. Okay. So this guy is once again in row echelon form. Whether or not it's in reduced row echelon form depends on this guy. If that guy is 0, then we're in reduced row echelon form. But I don't know what value it is, so we can't conclude. All right. Next example. There's no rows of zeros. We detect leading ones here and here. That's all well and good, but then we see this guy here, this 2. Okay, so this 2, this is not even in row echelon form. Okay, it's not in row echelon form because the first non-zero entry in that third row is a 2. It's not a 1. If I wanted to get this thing into row echelon form, I'd need 2 row operations, okay? First thing I'd have to do is I should take row 3. I'd have to multiply by a half, right? That would give me a leading 1 in the third row, okay? But that leading 1 would be to the left of the leading 1 immediately above it. We don't want that. Leading ones that are lower down need to always show up to the right of the ones that are above it. So I would also have to take row 2 and row 3 and swap them to get this sort of staircase pattern. Okay, so I would need those 2 steps to get that guy into row echelon form. Okay, the next one is kind of an interesting one. It's a matrix of entirely zeros. Is it row echelon form? Is it reduced row echelon form? Well, let's check the conditions. Are any rows of zeros at the bottom? Yeah, I mean every row is all zeros. I guess they're all at the bottom. right? There's certainly not, I guess this is a bit ambiguous here, but there are no rows of zeros sitting above non-zero rows because there are no non-zero rows. Is the first entry in any non-zero row a 1? Technically, yes, because there are no non-zero rows. Well, the third condition is also vacuous, right? And the same with the condition for reduced row echelon form. This is in reduced row echelon form, right? Because it trivially satisfies all of the conditions. What about this next guy? This next guy is also in reduced row echelon form. A lot of people will be thrown off by these guys here, okay? Don't worry about the fact that there is not a leading one in that column, right? It's row echelon form, reduced row echelon form. We pay attention to the rows, right? There are no rows of zeros. Okay, the first entry in each non-zero row is a 1, a 1, a 1, and those ones go down and to the right. So they follow what they should follow, and it's reduced row echelon form because each leading one is the only non-zero entry in its column. Okay. Similarly, this last guy is also reduced row echelon form. Okay. You got your row of zeros is at the bottom. The first entry in the two non-zero rows is a 1. The first non-zero entry is a 1. And those ones are the only non-zero entries in their respective columns. So it's in reduced row echelon form. Okay, so far so good. Where do we go from here? Well, once you've got your matrix in reduced row echelon form, you need to be able to tell me what the solution to the system is. So you want to be able to do this quickly. You want to be able to just glance at that matrix and tell me what is the answer. Okay? So look at this first one, right? What does this first row, so let's label these columns, X, Y, Z for all three of them, okay? The X column, the Y column, the Z column. What does that first row represent? That first row says 1 times X plus 0 times Y plus 0 times Z equals 1. Remember these guys over here, those are the constants on the other side. Okay, well that's a very complicated way of just saying X equals 1. Right? The next row, similarly, 0x plus 1y plus 0z is minus 5. Y is minus 5. That last row, 0x plus 0y plus 1z, z equals 2. Okay, we've got our answer. What about the next one? So in the next example, the first row says x minus 2z equals 4. The next row says y plus z equals 5. The third row just says 0 equals 0. It tells me nothing, right? Really, this just says this is 0, this is 0, 0 equals 0. Yes, that's true. Right? So the third row contributes nothing. And so I haven't said anything about what z is. And so what we do here is we just say z is free. And one of the things that we often like to do in this case is we might do this. We might say, let's let z equal to t. Okay? And we think of this t is called a parameter. It's a free variable. So this is called a parameter. And in terms of that parameter, we get this solution. We get x equals 4 plus 2z, but z is t, so x is 4 plus 2t. Y is equal to 5 minus z, so 5 minus t. Z equals t. And you can understand why we might call this thing a parameter, because what you have here, these are parametric equations for a line, right? Remember, what is it? It's a line that passes through the point 4, 5, 0 with a direction vector of 2, minus 1, 1. Right? So that's a line in 3 dimensions, hence parameter, right? Because it looks like parametric equations for a line. And one of the things that tells us is we can interpret the solution to this system geometrically, right? So geometrically, the solution to this system is a line in 3 dimensions. It's a line passing through a given point in a given direction, and every point on that line represents a solution to our system. Okay, now, the last one, this is one of the things you want to be on the lookout for when you're solving a system. If this shows up, we don't bother writing down anything because that last row says 0x plus 0y plus 0z equals 1. And you ask yourself, all right, are there any values of x, y, and z that can make 0x plus 0y plus 0z equal to 1? And I hope your answer is no, because we certainly know that 0 is not equal to 1. Okay, and so what does it mean in this case? If you see a row like that with zeros to the left of the bar and something non-zero to the right, that means that there is no solution. Okay, you just write that down straight away. No solution. Don't bother. Yes, the first row tells me that x equals -4. The second one says z equals 3. Who cares? There's no solution. Those values tell me nothing about how to solve the system because, to solve the system I have to solve all equations, and I can't satisfy that last equation. So there's no solution. There's no way to solve this system. Okay, so here is the Gaussian algorithm, okay, for solving a system, the so-called forward steps. We'll talk about, there's kind of two sets of steps that we do, but we start with the forward steps. So you start in the upper left-hand corner, and you work down and to the right. So you go from left to right, top to bottom, right? And so if you're programming a computer, well, one of the things you'd have to say is okay, is it the zero matrix? If it is, you do nothing. You can't simplify the zero matrix, right? But it's probably not the zero matrix. So if it's not the zero matrix, then you find the first column. There's got to be a column that has something non-zero in it, right? And you find the first column containing a non-zero entry, all right? And you make sure that at the top of that column, the first entry in that first non-zero column is a 1. So you use elementary row operations of your choice to get that leading 1 at the top of the first non-zero column. Once you've got that leading 1, you get rid of anything below it in that column. So that first column should be a 1, right? So your first non-zero column ends up looking like 1 and then 0 and then 0, zeros all the way down, right? And then you move on. Once you're done with it, by the way, you stop working with that column. You leave it alone, you move on to the next one, and you keep repeating until you're done. Okay? So here's what it looks like. All right. We've got an augmented matrix. We want to reduce it down to row echelon form. We won't worry about reduced row echelon form yet. Okay? So the first thing I could divide row 1 by 2, but the smart thing to do here is probably swap row 1 and row 2. Okay, 1, 3, minus 1, 4, 2, minus 1, 3, 1, minus 1, 1, 0, 2. Okay, and so now I've got my leading 1, and I'm going to use my leading 1 to create zeros. So what zeros do I have to create? I've got to create zeros here and here. So to get rid of that 2, I'm going to have to do row 2 minus 2 row 1 and make that my new row 2. To get rid of that 1, I'm going to have to do row 3 plus row 1 and make that my new row 3. Okay. Notice I'm doing 2 row operations at a time, but they affect different rows, so I can get away with this, and it saves me a little bit of writing. So we don't change the first row. Let's leave that guy alone. Okay. So now I'm going to get rid of that 2. 2 minus 2 gives me 0. Minus 1 subtract 6, I get a minus 7. 3 subtract minus 2, 3 plus 2, I get a 5. 1 minus 8, I get minus 7. Okay. Now I add row 1 to row 3, minus 1 plus 1, 0. 1 plus 3, 4. Okay, 0 plus minus 1, minus 1. 2 plus 4, 6. Okay, so now you're done. You've got that first column, right? 1, 0, 0. So here's the thing. Once you've got that first column, you've created that leading one and the zeros below it. Stop working with that column, and that means you got to stop working with row 1. Okay, so we leave this stuff alone. We leave it alone. Okay, it's part of our matrix, but we ignore it, and we kind of boil things down to this smaller matrix, right? This matrix now is so basically we started with 3 equations, 3 unknowns. Now we're down to 2 equations, 2 unknowns, right? So we ignore that first row, first column, and we deal with this smaller system. This is the idea with the algorithm. At every step, you're cutting things down to a system of a smaller size. All right. So now we repeat the algorithm for this 2 by 2 system that we have left over. How are we going to do that? Well, one option would be to divide row 2 by -7, create my leading one that way, but then I'm going to get a -5/7 there. Maybe we're not so keen on those fractions. So one of the things I might notice if I'm paying attention is, well, 2 times, I've got a 4 sitting here, 2 times 4 is 8, adding 8 to -7, that gives me a leading one, right? So this is not necessarily, from a computer's point of view, this row operation, doing row 2 plus 2 row 3, oops, and making that my new row 2. This is technically a deviation from the algorithm that you would give a computer. The computer would divide by -7 because that is the most efficient way of doing things. But as humans, we tend to prefer to avoid fractions if we can. So -7 plus 8 gives me a 1. 5 minus 2 gives me a 3. Okay, -7 plus 12 gives me 5, 0, 4, -1, 6. Okay, all right. Now I've got 2 leading ones. What's my next step? My next step is I've got to get rid of any non-zero entries below my second leading one. That means I got to get rid of the 4. How do I get rid of the 4? I should do row 3 minus 4 times row 2 and make that my new row 3. And again, because I've got zeros to the left of that leading one, I don't have to worry about what happens in this first column, this highlighted column, right? These guys here are still, they're still out of bounds. We're not dealing with those, right? They don't come into the picture. 1, 3, -1, 4. I'm not changing the second row. 0, 1, 3, 5, 0. So I get my 0. 3 times -4 gives me -12. I'm adding that to -1. I get -13. -4 times 5 gives me -20. Added to 6 gives me -14. Okay. All right. So now I kind of hive things off like this, and I'm just left with a 1 by 1 system. There's only one thing left to do at this point. There's only one thing really that I can do. I got to divide by -13. Create my last leading one. I've got no other choice here. So I do -1 over 13, row 3. That's my new row 3. 1, 3, -1, 4, 0, 1, 3, 5, 0, 0, 1, 14 over 13. And we're done. That's in row echelon form. We could, if we wanted to, we could continue on to reduced row echelon form from here, but that's a topic for the next video.